Come on in, everyone. Sorry about the little delay, but still a delay. Anybody have any questions? It's technically after class has started, but I always want to ask questions. So if you have any about anything that happened last time or anything like that, just let me know. You can chat them, type them in the chat window, or you can ask me out loud. Saying I might have hit mute on you by accident. I was trying to hit unmute on my own screen and I hit yours by accident.
Professor, just to clarify, is so the test is going to be next week? Because I believe in the calendar for the lab, it shows the next week as the flex day.
Yes, it should be yeah, because you guys meet on Tuesday and the turnovers on or no, you guys meet on yeah, you do meet on Tuesday. So yeah, it should be exactly Tuesday a week from today. I will put up the practice test for that, but yeah, that's the next online test. Let me double check my calendar. Where's my calendar? There it is. Yes, so today's the 17th. Ah, yeah, that explains it because I had October 30th for my class that meets on Monday. Yeah, so that makes sense. Yeah, so the 24th is your next face-to-face test date during lab. Thank you, Gavin. I'm feeling a lot better. I'm sorry about the delay and having to miss and all that good stuff. Hopefully, I got the emails to you soon enough. I had one poor student, they got it, but I made it like 5 o'clock in the morning. I was sick and tired and sent it out, and it was like a 202 class, but I evidently typed 242 or 241 or something. So like immediately responded like an hour later to my text message, I mean to my email message and my text message and said, hey, I'm assuming this is a mistake because you said physics 241. Well, I was dead asleep and didn't wake up till 2 o'clock in the afternoon. So I didn't see that. The poor guy drove 2 hours, felt so bad. So I apologize if that happened to anyone, but I definitely didn't try to. I tried to make it as accommodating as possible. Thank you for asking, Gavin. Anybody else have any questions? All right. Well, we are deep in.
I do have, Professor, I do have a few questions
Okay, go for
regarding some of the formulas
it.
in the well, not these are specifically formulas that are not in the textbook, actually.
Okay.
Um, like just like in the process of doing like the last few like chapters of like homework and stuff, I've like there's been a couple of times where I like got stuck and I like went online for like help and stuff, and there's like I've stumbled across like upon some like formulas that are like people present as like, oh, this is a given. Like when they go to explain how to solve something, they'll be like, oh, we know this, and it's like
How do you know
the
that?
our textbook. Yeah, like how do you know that? Um, so
Gotcha.
like I
Any
think for the electric, like one, the electric field of a parallel plate conductor,
uh-huh.
they like Q over permittivity of free space times the area of the parallel plate.
Right.
I'm not even sure how to derive that from what we have in the textbook without like it taking me like a long time to do it.
Gotcha. Yeah, that is exactly the right equation, but it's the only difference between what I gave you versus what you have is I gave you sigma over epsilon naught uh is the electric field between the parallel plates. We got when we actually derived it using Gauss's law,
Okay.
we got sigma over 2 epsilon naught over an infinite plate. And then what happens is the positive plate creates a electric field pointing away from it. And then the negative plate next to it creates an electric field pointing towards it. So both of them are parallel. So you end up adding sigma over 2 epsilon naught plus sigma over 2 epsilon naught, which gives you sigma over epsilon naught. Now, here's the
So
weird part.
the
Yeah, go ahead. You might have figured it out already.
well, I was gonna you said that you gave us sigma over epsilon naught, but like you're saying that we derived that.
Yes, we
Because
did.
I didn't see that one in the textbook either.
Okay,
All
yes.
right.
Yeah, they do that in the text. We did it once with the Coulomb's law in integral form, but what we did was directly above a circular disk of radius r, and then we examined what happened when the radius of the disk was way greater than the distance z above, and then that formula reduced to sigma over 2 epsilon naught. And then, like I said, the sigma is technically q over a. So that's why you saw q over a epsilon naught or q over epsilon naught a, because sigma is just q over a.
Okay.
So yeah, you actually did have it. It just, it might not have smacked you in the face like you'd like it to have.
Yeah. I these last few chapters that has kind of been the case. Like just I spend 3/4 of the time that I'm like working on the problem, just trying to figure out what formulas to use.
Gotcha. So
And then,
go ahead. I'm sorry, I didn't mean to cut you off.
well, I mean, that's basically the end of that thought.
Gotcha. So that is what you're experiencing is very common, and I will tell you it's mostly a result of sometimes students don't understand what part is derivation, what part is problem solving, and what part is derivation just so you'll know where the equation came from, as opposed to derivation that you're supposed to do. That is always an ongoing problem with courses. What I've determined is most helpful for my students in general is going through the book in a given chapter and at least paying attention to the equations that they write as numbered. So those ones that I tell you you're allowed to use on your test, those are really
Yeah.
what we're going for.
Okay. It's
So
just like, I don't know, in particular the last chapter, like a lot of the homework, it wasn't like the vast majority of the questions weren't using the formulas that we have in the textbook. It was some sort of derivation
yeah,
of like 3 or 4 of them combined.
yeah, and that's actually way more normal for this level course. If you were taking the algebra-based physics, for instance, it would be a lot more
Yeah.
just applying the formulas. But yeah, a lot of times in the 241, 242 sequence, we do have where you have to combine 2 equations or 3 equations to get the ultimate equation that you want. And that's just supposed to be a quote unquote more mature level of physics problem. That doesn't mean it's necessarily not shocking and all that good stuff. So, it's perfectly normal for you to feel that way. Just keep an eye on exactly what ones you're doing when you're solving the homework problems. And they're generally a little bit higher level or more difficult level of problem than I do on the tests. So
Okay.
try to keep in mind that they don't always expect you to derive the formulas that have the numbers next to it. But in the cases where I've shown it to you, a lot of times it is, and I specifically try to tell you that. But some of them, yeah, you do have to actually figure it out on your own.
Okay.
Okay. Okay, so we're actually in chapter 25. I wanted to go ahead and knock that out. I have some specific problems we're going to work with regards to that. Does anybody else have any other questions before we get cracking on that? Okay, it looks like I gotta do something else with my iPad, and my dogs are unmonitored with because my wife's away. So this is probably going to happen a lot. I hope it doesn't, but there's a good good reason to believe it will. So I apologize in advance for them barking, pains in my rear end. But anyways, I'm going
Professor.
ahead and open up the document, and today's the 17th, right? Okay. I'm getting ready to open up the document that I'm using on my iPad, and I want to share the screen with that. It doesn't look like I have any other questions popping up, so I'm going to do share screen, share like this. And I'm going to pull this up, share screen. So if, by the way, on that question that you had, if you want to point out any of the particular problems that you had issues with, there might, because I'm not used to that being that many where you have to use multiple equations to get where you're at. But I haven't looked at that homework set in a little while, so it could be that. But if you let me know exactly which ones on which assignment, I'll look, and there might actually be quote unquote an easier way to do it that doesn't involve all that, and it might involve something like another equation that we derived. I'll let you know on that one. And of course, we got a week for the before the next test, and this chapter should definitely be on it, so that might be relevant to you. So yeah, if you the best thing is like send me a screenshot of the actual problem and tell me what homework set it came from in case I have to look up and see if there's any errors in it or stuff like that. So I'd need to know the homework set and ideally which problem, but if you don't know which problem, at least give me the homework set and that'll be fine. All right, so the problem that I wanted to work first was one regarding resistivity and temperature coefficient. And what it is they're telling you that a certain material has a temperature, or excuse me, has a resistance of 164.2 ohms. So R 0 is equal to 164.2 omega. And then that is technically supposed to be at 20 degrees Celsius. And then there's an RT at some temperature we don't really necessarily know, but that's what we're trying to figure out. That one has a temperature, I mean, a resistance of 187.4 omega. And that's at T equals question mark. And what they're trying to get you to figure out is what is the temperature. So this, for instance, could be a material like you'd use for a thermistor or something like that. And basically, the fact that temperature depends on, or excuse me, resistance and resistivity depends on temperature tells us that we can use resistance or resistivity as a variable that can measure temperature for us. So for instance, if you have a really precise way of determining the resistance of a particular chunk of wire, then you can actually put that chunk of wire in a situation where you know where you want to know where the temperature is and determine its resistance, and then use that resistance figure to figure out exactly what the temperature is in there. And that's what we're doing here. So the formula we gave you was the resistivity at a temperature T is equal to the resistivity at a particular temperature T0 and times 1 plus alpha times T minus T0. That's the formula. We also know that R is equal to rho L over A. So if you combine these two, solving for rho, you get rho is equal to RA over L. Now we're saying the wire doesn't appreciably change in size by changing temperature. Of course it does. I mean, all materials change a little bit in size, but we're not going to expect that to change very much. So we'll put this in, and now the formula becomes resistance at T times A over L is equal to the resistance at T0 times A over L times 1 plus alpha T minus T0, like that. So you can see from this that A is going to cancel out, the L is going to cancel out, and we have essentially the same formula that we did for rho, we now have for R. So that gives us, and your book actually gives this equation as well, but I just wanted to show you that it need not bother you switching so quickly, because even if you forgot that it was that way or didn't know it was that way, you could figure out that it's going to be this way just by doing this process that I just did. So what you saw there was sort of a pseudo derivation. That's me showing you for understanding purposes but also for showing you in case you forget. I would not necessarily ask you to do this on a problem, but I would highly expect that someday during some problem, you might not know that there's a formula for R instead of rho. And this is how you would maybe make an argument that you could use this formula. And you would actually be right in that case. So now we can plug all this stuff in. Here's the solution. Obviously, I've already begun the solution, but the resistance at the temperature is 187.4 ohms. And the resistance at T0 is 164.2 ohms. And that's equal to 164.2 times 1 plus. Now the alpha, I actually had that and I forgot to write it down. Let me get that real quick. Oops. Working on it. Hold on, folks. Sorry about that. The alpha for this particular thing is, I looked it up, it's for platinum. So let's see, alpha platinum is equal to 0.003927. And the units of that are reciprocal Celsius degrees. So it looks like that. So I'm going to put in here 0.003927 Celsius degrees to the -1 power times T minus 20.0 degrees Celsius. And then we'll close the bracket. Now, the first thing I'm going to do in an attempt to solve for T is I'm going to divide both sides by 164.2. And what I get is 187.4 divided by 164.2 gives me 1.14129, very close to the square root of 3. Actually, no, not close. I misread the number. 1.14129. Notice how I kept extra digits. This one had 4 sig figs. I'm keeping 1, 2, 3, 4, 5, 6, 2 extra sig figs, and that's pretty good. So I'll just keep it by underlining it like that. That's what we have, but now that's equal to 1 plus 0.003927 Celsius degrees reciprocal T minus 20.0 degrees Celsius. Okay, when you subtract T minus 20 degrees Celsius, that's what we get. That's how we get C Celsius instead of Celsius C. Or excuse me, instead of this side we get degrees Celsius degrees instead of degrees Celsius. That's just a convention that we use to help ourselves. So what I'm going to do now is I'm going to subtract 1 from both sides. That's going to give me 0.14129. And now I've only got 1 extra sig fig. So I'm going to add another digit that I had, which I can put back here to make it make more sense. So now that one's going to be like that. And this is now equal to 0.003927 times T minus 20.0 degrees Celsius. So now all I got to do is divide both sides by 0.003927 Celsius degrees reciprocal power. Like that. So I'm going to divide that number by 0.003927, and that's going to give me 35.979. Oops. Now that gives me back to 6 sig figs. So I'm going to underline these two. And I now realize that I should have Celsius degrees as the unit here. And the other side will be equal to T minus 20.0 degrees Celsius. So you can see T is actually equal to 55.9794 Celsius degrees, which you could also call as degrees Celsius, because that, again, is just a convention and a trick we use. So properly stated, we really should say that's 55.98. So this would be the actual answer with proper sig figs. But I try to set up everything where you don't have to actually keep your sig fig rules that solid, but it always helps in the homework system to do it. So does anybody have any questions on that one and how we did what we did or why we did what we did? All right, so that's one of the types of problems that I wanted to make sure I solve for you guys. Now, another part that we're going to at this point is we just covered basically resistivity. We use the idea of resistance being R, being rho L over A. Now we're also going to go into, instead of the resistivity stuff, we're going to go into electric power and how a house works. So I will tell you, your book actually does the derivation, but I want you to know, killing this, that as far as power goes, power is equal to, usually the symbol P is what we use, and it's dW over dt. You could, for instance, say that this is equal to d by dt of qv if you wanted to. And if you did that, then you'd say, okay, well, that's dq, or let's say d lowercase q. Let's get an eraser out because that looked bad. All right. So that equals dq over dt times v, which is IV. And that's actually one of the formulas. So that is, again, a pseudo derivation. I'd need to talk a little bit more about some of the specifics of what's going on here, but this actually gives you the right formula. So in that sense, it's at least something that gives you an argument for what the right formula is. So I want to express to you that the power, and notice the wording here. It's important that you understand the proper wording with currents and voltages and resistances and stuff like that. What this is saying is the power dissipated by an electrical wire, resistance, object, anything, okay, is equal to the product of the current going through it times the voltage drop across it. Okay. Notice I said the current going through it multiplied by the voltage drop across it. Now, if we also use the equation given to us by Ohm, which is called Ohm's law, we get V equals IR. So if we, for instance, don't know V, you can replace it with IR and you get I squared R. In this case, what we're saying is the power dissipated by radiation, by heat being put out by the object, is equal to the square of the current through it multiplied by the object's resistance. Okay. Now, you also might, instead of not knowing the voltage, you might not know the current. So we could use Ohm's law again to solve for the current, and the current would be V over R. So instead of replacing the V in the first equation, we'll replace the I with V over R. And in that case, you get V squared over R. And that's really your three equations for power. And let me read that last version. The power dissipated as heat by an electrical device is equal to the square of the voltage drop across it divided by the resistance it has. Okay. So it's important to just understand those words. For instance, when we talk about high tension power lines, they use the phrase tension when they say high tension, and that's just supposed to mean high voltage. But when you're talking about, for instance, power lines going from, let's say, a power generating facility like a coal-fired power plant, you send that electricity out to various neighborhoods and you send it along wires that often you've seen out in country fields and mountains and stuff like that, where they're up on a really tall tower and the wires are really, really high, and they stand on that tower that sort of looks like a man with no arms, but he has shoulders and deltoids. He's got short legs and no head. Okay, so those towers are that high for a reason. And the reason is they've discovered that it's much more efficient to send that power out from a coal-fired power plant or a nuclear power plant or whatever at extremely high voltage. So it's not uncommon for those wires that are up that high above the ground to have voltages on the order of 250 volts, even as high as 1.5 million volts. Okay. But that's not the V that we're talking about here. That's not the V that's used in calculating the power loss. The V that's used in calculating the power loss is, let's say we put it in at 1,200,000 volts. And when it gets to the substation where they're going to break it back down from 1.2 million volts, instead of being 1.2 million volts, it might be 1,199,950 volts. So that difference between 1.2 million and the number I just said, that's the V that we're talking about. Does that make sense to you folks? So I just want to make sure you know that, because that's sort of the whole thing when I make an argument to you that we have discovered it's much higher or it's much more efficient to pump the voltage up to extremely high voltage, because extremely high voltage means that the current will go down. See, if you look at P equals IV, what you can think of is when you go to a transformer, which is a device that turns electricity of one voltage to either a higher voltage, in which case it's a step up transformer, or to a lower voltage, in which case it's a step down transformer. The best you can do with that transformer is not lose any power. So that means I1 V1 is equal to I2 V2. So let me write that off here to the side. So imagine I1 V1 is equal to I2 V2. Now, in reality, I2 V2 is actually going to be slightly less than I1 V1. Let's not worry too much about that right now. I just want to let you know that in reality, you can't, do 100% efficient transformer, but you can get really close. And power companies have done a really good job at trying to do that. So if I decide that I don't want my voltage sent out at 125 volts, which is, or actually 170 is the peak to peak that we use in our house, then we might take I1, which was, let's say 170 volts. And let's say we're actually supplying 10,000 houses. Well, I should have put that in a different way. If we're supplying power for 10,000 houses, each house gets 200 amps. So 200 times 10 to the fourth would be 2 times 10 to the sixth. So the current would be 2 times 10 to the 6 amps is what we're sending out, and from the power plant. And the voltage is what we're sending out is 170 volts from the power plant. If we wish to actually pump the voltage up to, let's say 2 million volts, then what you can see is the current I2 is going to be whatever solves this equation, which again, if we say V2 is 2 times 10 to the 6 volts instead, then you can see that I2 is only going to be 170. And then if you look at this version of P right here, you see that my current went down by a factor of basically 10 to the fifth. And I squared times 10 to the negative fifth gives you 10 to the negative 10th. So we've saved about 10 to the negative 10th times power. So that's the whole point of or that's one of the whole points of us using step up and step down transformers to transfer electricity. We're set because each house gets a 200 amp service on average. I mean, you can ask for more if you want, but a 200 amp service is sort of standard. So we're set by the number of houses that we're doing and by how far away it is. That tells us how much amps are going to have to happen. And that also tells us essentially what the resistance of the wire is going to be, because you basically have resistance is rho L over A, and you're either going to use copper or aluminum. Aluminum is lighter, but less conductive, but not a whole lot less conductive, but also a lot less expensive than copper. So yeah, you'll probably use aluminum, and you just take the resistivity of aluminum, multiply it by the distance the wires are going to have to travel, and then divide it by the cross-sectional area of the wires. And that resistance is going to be fixed whether you're carrying it at 170 volts or 2 million volts. So that R is fixed. All you can really do is try to affect the I squared. If you tried to affect the V squared in the other part of the formula, that's still tied to the resistance of the wire. Remember, the V is the voltage drop from one end to the other. So you're not going to be able to capitalize on the V squared over R, because that V is not the 2 million. The V is the, 50 volts drop that it gets from one end to the other. Anybody have any questions on that?
Yeah, why don't we call that V delta V then?
We sometimes do, and you can. So sometimes people will literally write Ohm's law as delta V is equal to I times R, but usually they write V equals IR. And really, that's all of those are supposed to be voltage drops, but it turns out that we've never really thought of it too much that way, and we just keep using the same symbols. But that's a wonderful point. Keep it in your brain and let you realize that that's also what Ohm's law says. Ohm's law says a object in an electrical circuit has a voltage drop across it equal to the current through it times the resistance it has. So that should be a delta V as well. So yeah, completely keep that idea. That's good. You've sort of realized something about physics that's kind of a crappy. But knowing that it's crappy, you can now adjust for it. And if you want to, you can call it delta V all you want. That makes sense? So good job on that. So that's the power, and that's me showing you how helpful that is. So this process, by the way, of stepping the voltage up from 170 to 2 times 10 to the 6 volts, basically what you have to do that is you take 2 times 10 to the 6, 2e to the 6, and I'm going to divide that by 170, and I get 11,764. So if I wanted to do that step up, I'm going to show you exactly what's required, even though we're a little early on that. So if I wanted to step up from 170 volts to 2 times 10 to the 6 volts, what we'd have to have is essentially a Pilgrim's belt buckle that you know from grade school when the Thanksgiving play would come out. Okay, so you've got that little Pilgrim's belt buckle made of iron, like this. And what's going to happen is this will be the voltage coming in. And let's say it's 1,000 turns on this side. and this is VN, is 170 volts. Now, in order for it to come out as 2 million, this would have to be 1,000 times 11,764, which is approximately 1.18 times 10 to the 7 turns. So 170 would come in, and out would pop about 2 million volts. But literally just making the number of turns 11,764 times higher will make this voltage step up from 170 to 2 million. That's called a step up transformer. And it works really well, specifically because we're in AC. If we tried to do this with DC, it wouldn't work. Okay. There are other ways of stepping up and stepping down DC, but we ended up not choosing to go with DC. So it's a lot less common for us to figure out ways. In fact, I haven't even looked it up in a while, so I don't even remember how we step it up and step it down. The main thing is, well, I can think of a couple ways, but they're probably the most inefficient ways ever. But that's the way you can do it. And therefore, when you leave the power plant that's generating the electricity, no matter what it's trying to send out, they're probably going to bump the voltage up. And when the voltage goes up, the current goes down by the exact same factor. So in this case, the voltage is going to go up by a factor of 11,764, but the current is also going to go down. So I should say voltage went up by a factor of approximately 11,764, but P equals IV tells you that I went down by a factor of 11,764 too. So that's the fact that the current went down is really what we were shooting at, because that means P equals I squared R implies that the power lost. And remember, the wire's getting hot and heating up the atmosphere contributes to global warming in some sense, but also it's just wasted energy. I mean, you put in a certain number of joules, you're getting out less joules, and the more of that heat that goes out, the more of those joules and the less of the money you're getting. So in this case, the power loss is going to go down by a factor of 11,764 squared. So you can see that's pretty big. That's actually a factor of 1.39. Actually about 1.38 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, but times 10 to the 8th. So you're saving a butt ton of wasted energy by stepping it up. Any questions on that? All right, so hopefully that was helpful. The next part that we want you to understand is really electric power the power in households. So specifically, I want you to understand exactly what's going on with the electricity in your house. I will tell you that the electricity in the house is in fact AC. So if you made a plot of voltage on the vertical axis and time on the horizontal axis, what you would get is something that looks like this. Okay. And in fact, this quantity would be called V0. And down here, this would be negative V0. And the voltage as a function of time would be V0 times sine of 2 pi f times t, which we also call V0 sine omega t. F in the US is equal to 60 hertz. A lot of countries actually use 50 hertz, but we use 60 hertz, and that's what goes in right here. And a hertz is also a cycle per second. And a cycle would be from here to here. Like that. But it could also be, for instance, from here, skip one of the same height and then go to here, in which case this is one cycle. Like that as well. So that's what a cycle is. Now, you know, V is equal to IR. So I is equal to V over R. So guess what? That means I of T is equal to V0 over R times sine of 2 pi F times T. And as long as you're dealing with batteries and resistors, that's pretty much how the electricity is going to flow. The current and the voltage will be aligned, but that is not necessarily the norm. So for instance, the current in this case would look roughly like this, and I apologize for it not being smoother, but I think you can get enough out of it. This is V0 over R, and this is I in black. And this is negative V0 over R. But they would basically be in phase, and just, you know, difference in magnitudes, not only according to units, but also according to the number itself. So I'm pulling up a receptacle real quick because I never remember off the top of my head exactly how which wire is what. So I figured that this time I'd actually pull it up and we could see, or I could actually look at it in real time and then tell you. So it looks like this one might be good. So yeah, I'll do this. So another part of houses, I've already told you that, of course, we're going to have an AC circuit or AC electricity coming to us. In fact, instead of a battery, what you'd have is they use a symbol that looks like this. So you draw a circle and you put a little sine wave in there. And then you go out, and this would be like your first resistor or your first light receptacle, and then your second light receptacle, and so on and so forth. But that's basically how that works. So what I wanted to show you is what your actual electricity looks like, so you have, in some sense, what exactly is going on. So let me draw a receptacle. I'm going to try to draw it as well as I can. So these are the plugs, for instance, that you have in your house. There would be a little screw there. It's almost always a stupid flathead screw. I hate those things. You can also say this goes like this. There's some more plastic around here, some more plastic around here, more plastic around here, more plastic around here. And then there's all sorts of giblets, if you will. There's various things on the actual circuit that are kind of more helpful than you might know. So I'll walk you through that a little bit as well. But there's one big slit, and then there's a small slit, and it's not that big of a difference, but I'm trying to show it so you know it. And then there's an itty bitty mouth thing like that. And then, of course, there's a big slit again over here. And there's a small slit over here. And again, there's a mouth right here. Now, there's all sorts of cool stuff. So, for instance, when we close this off, what you'd see is there's actually a little metal bracket that sort of looks like this. And this little area right here, you can use to trim your wire. So for instance, your wires, when you go to connect them, you'll have basically a bare wire that comes out. There's also another wire that comes out. Now that part I'm just drew right there, that's the bare part, but there's actually a housing around it, and that housing would be white. And then there's another housing over here. And again, you got another bare part of wire, but this housing would be black. And then all of this is wrapped up inside of another wrapper, if you will, of polyvinyl chloride, basically a PVC type product. And that's the wire that you have. That's most of what you're running in. And then the gauges, of course, are very specific sizes depending on how much current you're using and all that good stuff. So you've got a bare wire, a white wire, and a black wire. There will be let me change colors real quick. There will be a green screw right here. And that's where the bare wire connects. Because the bare wire is going to be your ground, and that's actually what's connected to these holes. Okay. Now over here, you will also have a screw, which from this side just looks like a screw. And then there's another screw. So they just look like rectangles, basically. But these are stainless steel screws on that side, and they are connected with that hole. And meanwhile, let's see if I can do this right. On this side, oops. On this side, you'll have brass screws. Or at least something that looks like brass. Now, the way those work is basically you're going to take your wire that's black and coming from the circuit panel. That's also called the service entrance, where the electricity from the road hits the outside of your house is called the service entrance. And then usually on the opposite side of that same wall is the circuit panel, which has all your breakers. And if your house is old, you'd have all your fuses instead of breakers. But basically that's where the black wire goes, is right along and connecting to the brass screw. One of my students told me they have a mnemonic they use, and I apologize for the offensiveness if you don't like cuss words, but they say, what was the phrase he used? Black to brass saves your ass, or something like that. So that can help you. So that's where the black is supposed to connect. And then also from the circuit panel, you'll find there is another wire that comes here, only this one is white. So in this case, you have a white wire, and that's also coming from the circuit panel. Okay, so let me change it back to black and give a little bit of an outline so we can actually see what we're talking about. So the stainless steel is where the white connects to, and the bare is where the green connects to. So, and I made a point to say this is where we're actually coming from the circuit panel. So you know current's coming in from those wires. Now, what you do is, if this isn't the last receptacle on that certain circuit breaker, which is typical, for instance, in a bedroom, you'd have one light receptacle or one light socket, and then you'd have another one, and you'd expect all those light sockets to all be on the same breaker. So how do you run the next wire or the wire to the next circuit? Well, what you do is you now take a black wire and you run it from here again. It's going to be a black wire, but you run it from the brass side to the brass side over here on the next receptacle. And then, of course, on this side, you have the stainless steel screws. And what you do with this is you run the white wire from here. Oops. You run the white wire from here to here. Like this. Now, we normally call the white wire the neutral and the black wire the hot. Okay. So if you're thinking in terms of a circuit, what we'd say is there's this, and you sort of think of it like current is going out this way through the black wire, at least for part of a cycle, and then it goes up and hits the resistor, which is our receptacle essentially, and then the white wire returns. So in this case, you can think of it like let's do this. Actually, I'll just keep it this way. And what we're thinking of here, you might want to, just to make it a little less complicated, you'll say that's T and that's V. And what we're looking at is just this part of the wave. So for that first cycle, the current is going to the left through the resistor and then coming back in through the white. And then, of course, you can go on and have another resistor as well. Now, the next part is I'm going to draw my receptacles. Again, long, short, mouth, long, short, mouth. Oops. Sorry about that mouth turning out so bad. And then I'm going to change this mouth because clearly it pooped the bed. Okay. So I think with that, you can see that indeed what's going on is we have a power supply like this, and we have a black wire that goes out, hits a resistor, hits another resistor, hits another resistor, and all these resistors are potential loads that you plug into the light receptacle. And then on the other side is the white wires to return them. So I'm going to do it like this, and this, and this, and this, and this, just so it looks like there's a white wire there compared to a black wire over here, which I'll fill in. The main reason I did all this drawing is, one, to show you a little bit of how you connect your wires if you have to wire a light receptacle, but two, by seeing it, I think you can convince yourself that in fact the receptacles are all in parallel. Does that make sense to everyone now? Now, I'll tell you also, this receptacle has all sorts of cool stuff. Not only does it have that little thing where you can trim the wire, but on the back, there will be a little divot, and it will say, this is how long you're supposed to trim the bare wire. In other words, you cut the housing off the black wire and the white wire, and the amount of bare wire that sticks out of the black housing and the white housing is exactly this length that it shows on the back of the receptacle. And not only that, on the back of the receptacle, you'll see there's actually holes in it where you can plug the wire straight in instead of having to wrap it around those screws. But there's a lot of different ways to connect it. It also gives you, of course, by having the holes in the back, that means you can take and connect one receptacle to the power supply by going to the top screws. You can connect another receptacle by going from the bottom screws to the new receptacle, but then you can take another set of wires out of the holes and run yet another receptacle. So it just gives you a lot of freedom. You're also supposed to, of course, curl the bare wire that you wrap around the screws in such a way that as you tighten it, that's actually tending to turn the brass bare wire in the same direction that you thread. In other words, in a clockwise direction called lefty loosey, righty tighty. Okay. So as I told you, that's actually the electricity. What I didn't tell you, I forgot to write right here, but V0 in America is essentially 170 volts. Okay. But it turns out, if you actually want to figure out what the voltage is, for instance, if you use a multimeter instead of like an oscilloscope to find out the voltage of an AC signal, it's going to spit out one number. And of course, if you look at the graph of the voltage as a function of time, you might wonder, well, what the heck does that one number of 120 mean? So in the US, a voltmeter reads V equal to about 120 volts. Well, that is called VRMS, root mean square, which y'all heard before from chapter 16 and all that good stuff. The main thing is what they're doing is they're taking the integral from 0 to t of v squared of t dt. And what that ends up working out to be is V0 squared over 2. So this is V bar squared, which you can also represent as V root mean square squared. In that case, I should probably remove this little overbar, but that's what that is. So we now have a neat expression that tells us VRMS is equal to the peak voltage divided by the square root of 2. Because remember, we got to take the square root of that to figure out what the actual voltage is. So this means VRMS is equal to the square root of VRMS squared, which equals V0 over the square root of 2. You can define the IRMS the same way. And in this case, I0 is just V0 over R in the way we had it drawn before. Let me completely change that. So that's just V0 over R. But that's what we actually use. And the main reason I bring that up at all is because it turns out when you go to calculate power in an alternating current circuit like this, and by the way, this section in your textbook, which is 25-6, so let me write this down here. That subsection 25-6 explains circuit breakers and fuses. So that's something that's really good to read. I don't have that much time to cover it, but it's very interesting. If you have any questions, make sure you ask me. But the deeper thing is there turns out to be a whole different set of equations that we use when we're talking about power and alternating current. So when we go to do that, we can see the alternating current works out like I said. But here's the neat part. When you go to calculate power, power turns out to be basically on average 1/2 I0 squared R. Notice that that looks just like the formula we had for the P equals I squared R power before for for DC. But in this case, what you can realize, since we now know how the root mean square is related to the peak voltage, we could say this is I0 over the square root of 2 squared times R. You see that that's equal to the 1/2 I0 squared R. So that means the average power for an AC circuit is in fact IRMS squared times R. It turns out that you can also use VRMS squared over R, and you can also use IRMS times VRMS. So if you use the root mean square values rather than the peak values, then your formulas for power don't change either. Any questions on that? All right. So that's what I wanted to cover regarding AC power, your house, how things are done, so on and so forth. But the rest of it that I want to do is a little bit more problems, and this will finish up basically, this will finish up chapter 25. Now, I will tell you that, yes, voltage and current are in phase for DC. So let's write that. Voltage and current are in phase. Now, just remember that means the peaks line up with the peaks and the troughs line up with the troughs and the center lines line up with the center lines for AC only with resistances, or I should say resistors, not capacitors or inductors. In fact, that's an important thing when you're starting to work with AC circuits. What you'll find is there's this phrase that goes Eli, the Iceman. Okay, this means current follows voltage in a capacitor, and it's by 90 degrees, which is of course pi over 2 radians. And this one means voltage follows current in an inductor. It's also 90 degrees, by the way. Okay, so that's something we'll deal with when we get to AC circuits, but I just wanted to give you that yes, like this drawing shows, the voltage and current are in phase for resistors, but if you actually did it for a capacitor, then Eli, the Iceman, ice tells us that the current is before the actual voltage. So in that case, the current through a capacitor would be ahead by 90 degrees. Actually, I should bring it all the way down. Like this. Okay. So it's been shifted forward 90 degrees, and that is I through a capacitor. Whereas let's try a different color. I'm going to say purple. And in this case, we'll find that actually I should turn this back here, go back here, and so on and so forth. And this is in a capacitor, or excuse me, in an inductor, this is actually the current following the voltage. So this is I inductor. Okay, so that's what I mean by it's actually lagging by 90 degrees. All right, and don't feel too bad if you don't really understand what that means. That's okay. We're going to teach you that later when, if I decide to cover AC circuits, we'll teach it to you later. The more important thing is we still got a little bit more material that I want to make sure we get through. And one of them is I need you to understand, for instance, if you have a space heater, let's say, let's go with it. A space heater is rated at P equals 1,875 watts when running, oops, in the US on 120 V/60 Hertz AC power. A, how much current does it draw? And B, in the UK, they use 240 50 hertz. What would be the power there? And more specifically, when we do the power, you were going to realize that that power is basically going to ruin it. So let's do the solution. Now we are talking AC here, so we know if we use RMS, we're good to go. So what I'm going to say is P is equal to IRMS times VRMS. So that gives me 1,875 watts is equal to 120 volts times IRMS. Sorry about putting them in a different order. I don't think it matters too much. Hopefully you don't get bothered by that. So IRMS in this case is 1,875 divided by 120, which gives me 15.625. Now, I really only had at most 3 sig figs, so these two are extra, and that would be the amps. But I also should say it's not uncommon for us, for your textbook, for problems in general to ask for the peak current. And of course, I0, remember, IRMS is I0 divided by the square root of 2. So I0 is the square root of 2 times IRMS. So we could also say this times 1.414, or let's just do square root of 2. And that gives me 22.097 amps. And again, those two are not sig figs, so I'll underline them. So that's another typical question that happens is not only do they ask you what is the current, but they specifically say, well, what is the peak current as opposed to the RMS? Now, in part B, if you want to actually find out how much power is done, well, the voltage is going to change, but the resistance should stay the same. So you could use, for instance, P is equal to I times V, but that could also be I squared times R. You just remember these are RMS values. Like that. Or you could use VRMS squared over R. So if you use this, you can find R for the heater is equal to 1875. Actually, I'm going to say clear that. I'm going to say 120 squared. And then I'm going to divide that by 1875. And that's going to give me 7.68 ohms. And that's going to mean that if you assume the resistance stays about the same, which isn't that good of an argument because it's going to get a lot hotter and therefore the resistance will probably be a little higher. So the resistance will try to save you a little bit. But the main thing is now we can say the power in the UK would be V squared, which is 240 volts squared over 7.68 ohms. So now I'm going to do 240 squared divided by 7.68, and that gives me 7,500 watts, which means it's going to be way too hot. In other words, you're going to burn up the little tungsten filaments in the space heater by running that high of a power through it. Now, we only got 3 minutes left. The last thing I wanted to show you was that if you use something we call the current density, so current density is equal to J, and we can even give it a vector quantity. And then the current I is equal to the integral of J dot dA. And the units of J, of course, are amps per square meter. So that's why it's dot dA, meaning a area. Well, it turns out that J can be written as 1 over rho times E, or instead of using 1 over rho, you could use the conductivity times E. And this is, in fact, Ohm's law microscopically. Okay, so that actually allows you to calculate, for instance, the electric field in a current carrying wire. Now, I will tell you that you can actually do a derivation, and I'll just tell you the results right now, and you can look at the example in the book. But if you take a chunk of wire through which a current I is flowing, and you cordon off a little part, say, whose area is A, and whose length is VD, meaning drift velocity, VD, times time. Okay, well, I is basically Q over T, or you could say this is VD. Actually, this is VD times delta T, in which case you could say delta Q over delta T. Well, delta Q is really equal to the number of charge carriers times the charge per carrier, right? So we could say the number of charge carriers is the charge carrier density times the volume, and then times E, because we know the charge carriers have a magnitude of E. Now, the N we could actually find as N would be equal to, or let me see, V would be equal to V sub D delta T times A times E. And now we could say I, which equals J times A, is equal to delta Q over delta T, which gives us N VD, the velocity, the drift velocity, times delta T times A times E. You can see that the A's cancel out. Also, you can see that when I divide that by delta T, the delta T's cancel out, and I get that J, which I can now re-represent as a vector, is the number of electrons per unit volume times the charge of an electron times the drift velocity. And then I got to put a negative in it because the electrons are moving one way, but the current's moving the other way. And that's the actual expression we're going for, and time's up. Okay. So that's the actual formula. Now, your book shows you a really nice way. If you take the density of the material like copper has a density of 8.9 times 10 to the third kilograms per cubic meter, then you can imagine a 1 cubic meter chunk of copper. And then you can say, okay, each atom is going to contribute at least exactly 1 electron. Then you don't have to change the N, which is the number of atoms per unit volume, to N sub E, which is the number of electrons per unit volume, because the multiplier for that is just 1, because it's 1 electron per atom. So Ne and N are the same thing. I'm talking about lower cases. So you can actually say, well, I know there is enough atoms in that 1 meter by 1 meter by 1 meter cube to weigh 8.9 times 10 to the third kilograms. And that's also 8.9 times 10 to the sixth grams. And you can divide that by the molecular weight of copper, which is 63.5 grams per mole. And that'll give you the number of moles per unit volume. If you then multiply that by Avogadro's number, that'll give you the number of atoms per unit volume. And like I said, the number of atoms is the same as the number of electrons per unit volume, and you're done. Okay. So that's kind of nice. Do look at the example specifically. I want you to look at the example, and I'll write it right here. Example 2514. I've worked it out on several of my videos in the past, so you can find versions of it on my YouTube channel if you'd like. But the main thing is just know how to do that. And we are done with chapter 25. You're free to go. I will wait for the last person to leave in case you have any questions. But thanks for coming, everybody. Don't forget, test next time during lab. Angelica, you have any questions?
No, I'm good. Sorry. Have a good night.
There's no problem. You have a good night too. Bye-bye. Bye, everybody. Gotta call my little baby Aussie. Hopefully Cindy will call me.